2 lectures left. Today, I'm going to talk about the formulation of this finite element method, like what actually goes on in the guts. Some of you have seen it in other courses, but this isn't a bad refresher, I think, just to put it out there. Friday, we're going to talk about then how to actually use a piece of software. I'll actually pop up my MATLAB here with that on there, and we'll go through and do some examples. Okay? Just so you can kind of be familiar with at least one package that's out there. All of them work in similar fashions. You just have to figure out what their toggles and switches are. I learned how to use this one in half a day, and I was like, wow, this is pretty amazing. Half a day is not that bad of an investment for the power you get out of these things. And sort of that's kind of what you're looking at, especially once you know what you're actually trying to do with it. Okay? So let's consider discretizing now with this thing. With finite elements. And in particular, let's consider a specific equation. And let me show you right away that there would seem to be a problem. Okay? R x y u equals f x y. Okay. It's second order. This is going to be, there's no time dependence right now. We're going to consider what's called an elliptic problem. We're just trying to solve for the field u, which is a function of x and y. We have non-constant coefficients. This is linear. And a couple things to note. 2 derivatives total in x, 2 derivatives total in y. Total in y. And we say we want to solve this. Now, one of the things that comes up right away immediately when you try to solve this problem is that last time we talked about approximating these solution surfaces, right? We're going to say, here's x, here's y. Here's a solution surface u. And what we're going to do is approximate this solution by patching together little triangles. Okay? And in particular, we said all we have to worry about is, carrying these points around on this triangle, the vertices of the triangle. We're going to make, for each triangle, we're going to say there is a representation there. So let's say, call this the u of I triangle. It's going to be something like a plus bx plus cy. We're going to approximate it with that plane. Okay? Now, one of the problems that comes up right away is you're going to take this, approximate this, and in this interior is, how do you find it? Well, it satisfies this partial differential equation. But notice the following. I'm approximating, why am I approximating, by the way, with this plane? Because it's easy. Right? It's a patching of the solution. It's just a plane. It's very simple. But the problem is when I try to patch a plane to this problem, look what happens. I have 2 derivatives in x. What happens if I take 2 derivatives in x in this thing? It's just 0, right? The first derivative in x gives you just b. Second derivative in x gives you 0. Same thing with you have 2 derivatives in y. In other words, you get no meaningful information from this thing if you use this. Because the 2 derivative terms, just suppose, for instance, for the simple case of p and q being 1, all this stuff becomes 0, and all you get is r of x u is equal to f of x. That's not the problem you're solving. You need to carry around information of the derivative. And doing this doesn't. 2 options for you at this point. One, you could say, well, how about if I use one of these, instead of the simplex, what do they call it, the complex? So I have more points on this triangle. So now I have, for every triangle, instead of 3 points, I have 6. That means I'm going to double the number of points. It's a lot. Okay? So if I double the number of points, though, then this thing becomes a plus bx plus cy plus d x squared plus y squared plus fxy. Now when you take the second derivative, information is retained. doesn't drop out to 0. So you could use this. This is one option for you. Another option is to do the following. This is typically what's done with second-order problems. And in fact, if you look at a lot of the commercial software out there, they typically don't do higher than 2 derivatives. Or at least if you look at their examples, almost all of them are 2 derivative examples. And here's why. You want to use this. Using this is very costly. Using this is nice, but there's a problem here because it doesn't retain information. But what I could do is I could take this problem and recast it. In other words, I could say, I'm going to look at the integral of this problem. I have 2 derivatives in x and 2 derivatives in y. Now, when you integrate something, you undo an integral. So the idea behind finite element methods really is to recast this problem using what's called the variational principle. In other words, this is the derivative of something. What is that something? If I can figure that out, I'm going to take away one derivative in x and one derivative in y, and all of a sudden this becomes meaningful again. Okay? All right. So, variational principle. Here's what it means. I want to find some function to be minimized. In other words, I want to find, in some sense, the integral of these governing equations, so that when I take the derivative of this thing, I get back that equations. But now, this is a generalization of what it means to make a derivative. Typically, we think of a derivative as just, you take a derivative, that's just, a slope. In particular, what we're going to do is we're going to minimize this function, and minimize means take the variations to 0. In other words, in the one-dimensional case, it means where does this happen? But now, instead of a function like this, I'm looking for its derivative being 0. I'm looking for all the functional space which minimizes this function. It's a generalization of what it means to be a derivative. We're trying to find the minimum function, not point, that makes this thing, so when I take its variation or derivative, to be 0. So the idea is you say, okay, let's consider some function over a volume, f, where generically we'll consider this thing to be some 3-dimensional space, okay, plus there's a volume and then there's a surface component, and this is going to be our boundary terms. So not only do we have to transform the equation itself, we have to transform the boundary conditions as well. Okay? And this boundary condition will also just depend on the function itself and its first derivatives. Now notice, I've done this so that this function here, I'm trying to look for the functional that only depends upon one derivative in x, y, or z. The reason I only want to depend on one derivative in x, y, and z is because when I come back to this problem here, I'm going to be approximating by this function, and I, at most, want to be taking one derivative of it. Or else, this thing is meaningless. Right? If you take 2 derivatives of this with any respect to any of your variables, it just is 0. It doesn't carry any information at that point. Okay? All right. So by the way, here's the beauty of this method. We're going to have some solution curve. And in addition to this, I have to specify the boundary conditions, because that's something I have up here. And for instance, let me draw now the xy plane. I can make a boundary that looks like this. Try doing that with spectral or find a difference, and you can't. This is why you use this method. You want to say, I want to discretize this. Well, what it does is it says, okay, well, just basically draw a bunch of points on this outside curve, and then interpolate with a line between points, and then start off making your computational domains with triangles. And the nice thing about this, too, is you could say, well, let me break up this domain into two pieces. On this side over here, I have some boundary S2, and over here is S1. So notice S1 is from here to here and has some boundary conditions, and S2 is from here to here. And I can make any kind of boundary conditions I want. So for instance, on S1, I'm just going to impose that u of xy is equal to some function xy, for instance. And on S2, I'm going to make something more complicated. I'm going to say that I have p times du dx cosine theta 1 plus q du dy sine, so cosine theta 2 plus g1 u equals g2, where g1, g2, q, and p are some specified things that are p and q are the same p and q up here. G1 and G2 are some specified functions. And this happens on S2, where theta 1 and theta 2 are, if you take a normal projection off this thing, so I've done theta 2 is here, theta 1 is there. So this is really a very, I can apply very complicated boundary conditions. I think that's the only point of this. Who cares what this is specifically? I can give you very complicated boundary conditions, and this method says, okay, fine, I'll handle them. Okay? Just as long as I stick to no higher than one derivative on the boundary. Okay? All right. Now, what does it mean? Variational principle. So this is what I'm trying to solve. This problem here on this very complicated domain where part of the boundary is this, part of the boundary is this. And I'm going to try to rewrite that problem in terms of its integral formulation, which is this is the volume piece, this is the boundary piece. This is on the surface of that volume. And the idea is, in the interior, this should capture my PDE, my governing equation, and this should capture its boundary conditions. And these should be functions of just one derivative, because then, once I make them functions of just one derivative, that linear plane that I'm trying to interpolate between points becomes meaningful, because I can take one derivative of it, no problem. Okay? All right. What does it mean, by the way, to take a variational derivative? Now, what does it mean to take the derivative of this thing? Well, this thing is a function of these different variables, and there's a definition of a variational derivative, which you want to say, I want to minimize this thing, which means I need to have this idea to minimize something, I have to take a variational derivative. It's a functional derivative. So I'm taking the derivative not with respect to some variable x or y or z, but with respect to the function itself. And so that's what these little deltas mean. This is basically just generalizing the idea of the derivative. And what this translates over to is what's called the Euler-Lagrange equations, which become the following. Let me write it all out. No. What it is you say, well, take my function f, take it's a function of phi, phi x, phi y, phi z. So what the variational derivative means is to say, and I want to take this thing to be set to be 0. So I'm taking derivative with respect to a function, and this function depends upon all these variables. Well, what it says is take the derivative of f with respect to 5x. So 5x becomes like our independent, or our variable that we're actually differentiating with respect to. So 5y, 5z, and phi are independent of 5x. So you take your f, you take this with respect to 5x, and then you take dx of that. Same thing here. Take the derivative with respect to 5y, take dy of it. 5z, dz of it, minus d phi d phi. Okay? So the idea is this really, in some sense, and the reason we don't teach this in calculus is because it's a little bit more complicated on some level, right? I mean, this is a higher level thinking in some ways. But really, this is just, really, in some sense, the derivative is just really a subclass of this thing here. Okay? This is the more general idea. The idea that you can say, I don't need to take a derivative of just a function like this, and if I want to minimize, set it equal to 0, and here's this curve, and set it 0 there. I'm looking now in some higher dimensional space. For instance, if you were to look at all points that go, for instance, if you're trying to minimize in classical mechanics, one of the things is there's a whole variational formulation of classical mechanics, F equals ma. Because there is this idea that if I throw this pencil at Chrissy and hit her in the head, the path it took to hit her in the head was the one that took the least amount of energy to get there, right? I would never do such a thing, of course. Well, I mean, I'd probably miss. I mean, that's what I mean. But the point is, how do you pick that path out? Suppose this is here, and there's some force field that's acting there. A particle going from here to here in time will pick out the path that's sort of the least resistance. Well, I mean, think about all the paths you could take. All these are paths that are traveling in this space, and which one gets picked out? The path that minimizes the amount of energy that's taken to get there. So maybe, in this case, it's something like this. Who knows what it looks like? But this path here, in some sense, is your path for which, okay? It's a functional space, right? Because you have all these possible functions that could go from here to here, and the one you're picking out is the one that satisfies that. Okay? So this idea of a variational principle based upon this Euler-Lagrange, in fact, Euler-Lagrange, where a lot of this came from, this formulation came from this classical mechanics, how to recast F equals ma as, in fact, not F equals ma and just doing it with derivatives, but recast it in terms of Hamilton's equations and Hamilton-Jacobi, and then Euler-Lagrange equations, which give you equations of motion, which are equivalent, but now cast in this environment of my particle takes the path of least resistance and therefore satisfies this equal to 0. So we're doing the same thing here. Now, as an example, one question you could ask then, that might be true. So you could ask, what is then the variational principle for this set of PDEs? Okay? Well, I'll tell you. Here it is. I of u is equal to 1/2. Remember, you're integrating over to some domain now. This was for a 3-dimensional space. Now you're in a 2-dimensional space. dx dy of, here is your f. It's p of xy times u of x squared plus q of xy times u of y squared minus r of xy u squared plus 2 f of x y u. Plus, you have your boundary term, and for now, let's just consider the second boundary. Okay, the S2, which is on the surface, and what it is negative G2 u plus 1/2 G1 u squared. Okay, that's your I of u. Where does this come from? You can ask that. It's a fair question enough to ask. You can say, I wrote this down, and I'm saying to you that this is my f. This is the term that fundamentally gives me the boundary. Well, the f, remember, is the thing I'm actually minimizing. And I'm saying if I minimize this thing here, in other words, this is my integral of my equation. So if I minimize this thing here according to this equation, I should get back my governing equation. So the question is, do you in fact do that? Let's look at just the f component. Because this here is the interior of the domain, where this interior should give me back this thing here. Okay, so let's run it through these Euler-Lagrange equations and see in fact if that's true. Okay, so you can see, by the way, as we go along in this thing gets messier and messier. But it all can be automated. So it's good to see once to know what the basic idea is going on. And then after that, just kind of like, oh, well, you know, just let the computer take care of it from now on. Okay? So how do you get this thing? Well, the idea then is, this is your f, this interior portion here. So your f in this thing here is p u of x squared plus q u of y squared minus r u squared plus 2fu. Okay? Now, the claim is then, oh, and there's a factor of 1/2 out front of all this stuff. I'll put it behind. The claim is that that f, when you take its variations, this is the integral formulation of the problem. Okay? So let's take the variation of it. What does that mean? It means, do this. This thing is a function of u, so it's df du. And what is u a function of? Well, u of x, u of y, and u itself. So what you end up with is d dx of df dux plus d dy d df of d uy minus df du. And that has to be equal to 0. Okay? So all I did was took this thing here. This thing here was a function of phi. Well, now it's a function of u. And it has no u of z components. It's not three-dimensional. It's just 2. So it's, you get this term, this term, this term. That's what I had here. Now, if I calculate this, what do I get? In theory, what I should get is back my governing equations. Do we, in fact, get that? So let's run it through there. All right. So what do you get? This is equal to d dx of df dux. So look at your f here and take derivative of this f with respect to u of x. Think of u of x as the one variable. U of y and u are independent. U of x only appears right there. If I take the derivative of it, what do I get? Well, the 2 drops down, so I get 2p ux. That's it. Times a half over here. So 2p ux times a half is just p ux. And then I have this d dx out front, so this is what I get. Hey, by the way, what does this look like? dx p ux, isn't that first term over here? So that's nice. dx p ux. This is pops one term out like that. What does the rest pop out? We have to see if it pops out the rest of the equation. Plus, second term, d dy of df duy. Well, the ui only comes in right there. So, pop the 2 down. You get 2q uy times 1/2, which is just q uy. That's just like before as well. Minus df du. Take the derivative of this thing, respect to u. Well, this is u of x, not u. Remember, u, ux, and ui are like independent. There's no u here, so derivative is 0. No u there, derivative is 0. Here you get minus ru squared. Oh, so if you take the derivative of this, you get 2u. So you get minus 2ru times a half, which just becomes minus ru. Right? And, sorry, one more term. Minus ru there, and then you get here 2fu. If you take the derivative with respect to u, what do you get? Just 2f times a half. You just get, right? And that's supposed to be equal to 0. So let's write it out. So then you get d dx pux plus ddy qui. Then here becomes minus minus, which becomes plus ru. And then you have minus f, which I take to the other side, becomes f. Okay? So, isn't that the equation I started with? Indeed, it is. Okay? So it's nice. So this then tells you that when I minimize this function, minimizing this big old mess right here gives me back my governing equations. Okay? Again, you could ask the question, why do we do this? We did this because we want to use a simplex here. We're going to use triangles where we want to approximate these triangles by this. Let's not forget why we're doing this. Otherwise, this is stupid, right? I mean, this is a lot of work to rewrite this thing. The only reason you rewrite it is because then you can get away with using these simplex methods because only have one derivative. I mean, sorry, they only depend on px and cy. And then when you write the problem, which is equivalent to this, in this form here, what do you see? Ux squared, uy squared. You know what ux is. Ux is going to give you, if you take the derivative of this thing, it's just b. You get a b there. In other words, it doesn't give you 0. You keep your information. And the problem before is if you took two derivatives. And now the problem reformulated in this form, do you see any two derivatives there? No. The most you have is one derivative, which means now you can use these simplex components, which saves you half the number of points. The only work it costs you is to rewrite the problem. But this is a one-time expense that you do at the front, right? And once you get it down, then you can work with the problem. If you choose to go with the complex interpolation pieces, then every time you do the problem over and over and over again, you're doing twice the number of points. That's always costing you more. Whereas once you write it this way, you get a better, cleaner system. You can run it faster every single time. Okay? So it's a one-time expense. It's just like when you do LU. You first have to get the LU matrices. That costs you order n cubed. But then after that, it's order n squared. It's a similar principle. Okay? All right. Everybody happy with this, or at least, you know, kind of okay with it? The recasting of the problem to the variational form is a very important part. Okay? Now, last comment about this. Suppose I had third derivatives here. Fourth derivatives. You can see it's going to make it a lot more complicated because even if I do this trick, suppose I go to fourth derivatives, even if I do this trick, you know, your recasting is going to have three derivatives. That means you've got to pick an interpolating function here that has up to, that survives after three differentiations. So something like an x cubed, right? That will survive three differentiations. So then you see, as your derivatives go up, remember, in all the problems we've considered thus far, what was the problem with higher derivatives? It always added numerical stiffness. In the Fourier transform, it added numerical stiffness because now you had something like fourth derivative gives you a k to the fourth. Well, k to the fourth gets huge. That's where the numerical stiffness comes in from there. When you do finite difference, right, your CFL condition goes like delta t over delta x now to the 4. Or, yeah. So every time you, in your CFL number then, every time you want to increase your accuracy, you've got to take your delta t down by a factor of, 16. So that's where you, and then you can see here, numerical stiffness comes in because if you rewrite the problem, you still don't get around the issue because you've got to make more complicated interpolating functions. Okay. All right, now let me erase some stuff. Let me see how much I want to erase. Probably a lot. I'm going to leave that up. Take this down. Okay. All right. So, the process. Yeah, I'll just erase this too. Some general notes. What we just did was called, we wrote the problem in the weak formulation. That's often the mathematical language associated with the process what we just did. It's called the weak formulation of the problem, which is its integral form. Okay? By the way, going to this weak formulation is also very nice for one other purpose, which is if you have a problem where there are shocks that develop. If you have shock waves in a problem, often with a nonlinear wave propagation problem, you'll get stuff that, you know, starts off like this and starts to curl over. There comes a time when that's no longer a function. Mathematically, you have to have it as a function, and so maybe you approximate this by a shock wave of some form. Now, this is typically a problem because if you solve the problem, a discontinuity like this is bad. But when you write it in the weak formulation, in other words, the integral formulation, when you integrate over this thing, that's not a problem. The beauty about integration is it just goes, yeah, so what? There's a bump. I integrated over it. It smooths over everything. It's like Michelob Light. Have you seen those commercials? Smooth over everything. I think there's a math guy on that marketing team. Yeah, there's even an integral sign on it. So, anyway. I just remember that commercial. It sticks out of my head. Smooth over everything. So anyway, that's another point where you can use this. 2. Once you write it in this weak formulation, you now say my solution, uxy, is equal to the sum of all these interpolating functions, where the weighting of the interpolating function is given by these gamma i's. So part of what you need to do is, what are the gamma i's? Okay? Because you know what these interpolating functions are, or we can talk about where they come from. So these are constants. We have to determine this as well. And so this is going to be our approximation. It's going to be a sum of all these patches of solutions. We have to get every single little solution. They're all associated with each other, right? Because, you know, all these triangles are connected. So all the points of the triangles are somehow going to be associated. Now, a couple things to notice. Some of these points, let's call it from m plus 1 to m, are determined by boundary conditions. In other words, every triangle that touches with one point a boundary has to satisfy that boundary condition. So for instance, let's assume a very simple boundary condition, that the solution is 0 at the boundary. Well, so for instance, if you're in a domain like this and you're doing all these triangles, what do you know? These pieces of triangle right there have to be 0. What does that tell you about their function? You know, they have to satisfy this boundary condition. So whatever touches the boundary has to first and foremost satisfy the boundary condition. So that removes some of your triangles out of the action. But the interior triangles now still have to be worked on. And let's call these gamma 1, gamma 2, all the way to gamma n. This is the internal structure. And how do we get these? Well, what we want to do is take, this is an important piece here. We've written this in a variational form. We know the solution has to minimize. We know that our solution formulation is the minimum of these equations, and so our solution also has to minimize these equations. So what you say is, well, I take my I over here, which is a function of u, and how do I determine the rest of these things? that. I minimize by taking the derivative with respect to each one of these coefficients, setting it to 0. That gives me the behavior in the interior. Okay? Everybody okay so far? All right. So the pain is coming to an end. Just a little bit more. And like I said, then we just, once you've seen it once, as far as sort of the interior of this thing, the important thing is that from an algorithmic point of view, this all can be automated. You give me a form of solution, all this stuff, and this is what these guys do with these codes. It would be a pain to calculate these things every single time. So people do it, they automate it, and then that's what you want to use. All right, so here's what my U is. Here's what I got to do to calculate my solution. All right, so what I need to do, here's what U is right here. I need to plug in, wherever I see a U, this expansion, this sum. So what do you get? I hate getting into too much algebra, but this almost can't be helped for this problem, because it's not always that insightful. So in other words, do your expansion, and what do you get? Well, you get 1/2, integrate over the area there, P, and then sum, everything squared, plus I'll drop the QX, the XY dependence, squared minus R, and then this becomes squared plus 2F like that, plus your boundary terms, there. That's what you get. So this is your integral formulation, this big old mess. Okay? Now, a couple important things to notice. You have both your solution and its boundary terms coming in. The boundary terms, of course, are going to affect the interior points, so they're all wrapped up together. And what you're going to do at this point is take this whole thing and do for every I, where I goes from 1 to n, the n interior points. Now, here's the claim. When you do this, all you get out of this process is AX equal to B. Okay? Where the matrix A, each component of A has row column is given by this alpha. B is some betas, 1, beta, so beta 1, beta 2, beta n. X is equal to what you're trying to solve for, which is gamma 1, gamma 2, gamma n. And to spare more pain, let's look right here. Right here are the formulas I've given. Yeah. Okay. Here are the betas. Here are the alphas. Couple things to notice. Look at the betas. When you do the betas, you have integral over f, some boundary condition, and look at this here, the sum over the boundary terms. So in the b, in this ax equal to b, the right-hand side b has all the boundary information, or has some of the boundary information for all the boundary interpolated pieces. Okay? And then here is what the matrix elements look like in the interior. This old mess here. Okay? So you see it's a real mess where these 5i, by the way, what are the 5i? Well, we've approximated by, remember these functions we worked on last time in class? nj, phi j, where the nj were those Lagrange polynomial coefficients. So the reason you write it in this form, because it's a nice formulation for doing this, but basically what you have is a little interpolating plane at every point. Okay? So it's just a big mess. Okay. But that's the basic structure underlying all these codes. So really in the end, then, when you come to a problem like this, that's the underlying theory of it. And the process of doing this then is requiring several steps. First, you discretize your domain. And it becomes clear from this formulation that what you want to do is separate out what are called the triangles. We call them T1, T2, all the way to T of n, which are the interior triangles. And boundary, let's call them boundary triangles. So when you discretize this domain to a bunch of triangles, all which touch the boundaries, and you have the interior points, it's important that you differentiate which ones actually touch a boundary, because then they have to satisfy very specific conditions, versus the interior, which are really part of this ax equal to b piece, which is I'm trying to solve it. How do I solve it? Well, it has to satisfy the equation, plus information propagates from the boundaries into it through the matrix A. Okay? All right. Once you get that, for L, right? These are all the boundary terms. Determine values at vertices on boundaries. In other words, if I have my domain, and here's my triangle approximating this, this triangle has 3 pieces. 2 of them touch the boundary. So, okay, what I have to do is for every triangle that has something that touches the boundary, go figure out for these 2 pieces, I know I have to impose certain conditions on them. The third one is interior. Right? So you have to separate what touches, which vertices touch the boundaries, and determine the values they're supposed to be. Now, once you do that, then you can compute A and B. These big matrices of vectors, your right-hand side in your matrix. Solving it's then trivial, right? Because then your solution is just that. And then part of your big thing is to plot this thing now. Remember, you did this expansion. Now you've got to actually say, well, this triangle lives here, plot its amplitude. This triangle lives here, plot its amplitude. So plotting is actually a little more difficult, too, because you actually have to patch together the solution. Every little triangle lives in a different space, and it has a certain value, so you have to go through and then make a big matrix which has all the data, so you can write a mesh over it or something like that. Okay? And that's pretty much it. That's the algorithm. Now, like I said, at this point, all you really want to do, all this can be automated very easily, and we'll show that in class Friday. And that's exactly what you want to do. But at least the underlying guts you've seen. You can understand that within this framework, there is a variational principle underlying this so that you can use these simplex interpolations, finite elements. Once you understand that, then you understand that, okay, I can write this problem then in the weak formulation, discretize into triangles, and for every triangle, I have boundary conditions to solve, and then the interior to solve, which is just a big ax equal to b. Okay? Important point is, remember, if you start thinking about the reason we went to this integral formulation is because we require double the number of points otherwise. So that means your A matrix is getting that much bigger, right? So, and what we do know is speed is going to be tied up directly with this here. You're going to have to solve this in order n cubed. Or you could do it LU. If this is a time-dependent problem, if this A doesn't change, then what you do is you solve this in order n squared once you get your LU. But speed is of the essence. So you want this A to be as small as possible. So going to a formulation, we have from 3 points on an interpolating function to 6 makes a huge difference computationally. Okay? So this is why we went through this whole, big old mess here. But that's a one-time cost, and frankly, you're going to put it on this software anyway, so who cares? Just do it, and then you're done. Okay? All right. So remember, beer, a week from today, we'll all take off. If anybody's in Guggenheim around 5, we'll take off from there at 5. And then we'll head off, and I'll send an email about the location. Okay? All right.